Hey everyone, welcome. Today I want to share with you guys this neat trick that I recently learned in economics. Now, I say that this trick is in economics, but it's only used in economics, but originally it's actually from operational research, specifically about optimization. So the trick is to use this method called Lagrange Multiplier to find the optimal utility according to certain budget constraint. But before we jump into this method, let us take a look at this following example on the screen, and then let's try to use the conventional way to solve it. So here we have this problem here. It says consumer's utility is this letter U, and it's actually a function of X and Y. The specific form is X times Y. So it's a product of X and Y. The consumer's budget, now we're talking about this constraint here, right? Because that's how much money this person can spend. It's $100. Now, what is X, what is Y, right? The price of X, that's one product, is $1. And then Y is the other product. And of course, it has a price. So P of Y, price of Y, is $2. So now the question is, what is the maximum utility? So in other words, we're talking about some sort of optimization problem. So let's write down the problem. Question is, what is the maximum utility? So now conventionally, when we solve this problem is we figure out the equation of the budget, which is constraint, and then we manipulate the equation in a way such that when we plug that constraint back into the utility function, one variable disappears. And then it becomes some sort of quadratic form, which allows us to solve it using basically high school algebra. So let me walk you guys through the conventional method. So let's start with this constraint, which is this budget here that is essentially $100. So let's write that down. Budget, letter B, this is $100. That's our constraint. Now this constraint is composed of X and Y, right? So in other words, this B is really equal to price of X times X, whatever quantity that is, plus price of Y times Y, whatever quantity Y is. And then all we have left is to plug in the numbers. Now we know from our problem statement that the price of X is $1, price of Y is $2. So let's plug that in. And if we plug that in, this equation becomes 1 times X plus 2 times Y, because those are the prices. And that means this can be simplified as B equal to X plus 2Y. And this is the function for the constraint, or it's also called the constraint function. So with that being said, this constraint function, X plus 2Y equal to B, which is 100, now can give us some sort of relationship between X and Y. We may not be able to solve what's X, what's Y just yet, but we do know there's some sort of linear relationship between X and Y. So what we can do is we can write Y using some sort of closed form of X. So let's try that. Here, we're going to rearrange the formula, and we're going to put Y on one side. So 2Y equal to 100 minus X. And then we're going to simplify it. So what that means is Y, let's leave that on the left-hand side. And we're going to divide this 2 over to the right-hand side. So what that means is this is going to be 100 over 2, subtract 1 over 2x. Now we can simplify this equation even further, and that will become y equal to 50 minus half times x. And that is the equation that helps us understand the relationship between x and y. Now, the question is, why on earth do I want to do this? The reason I want to do this is because let's look at this utility function just a little bit. It has two variables, right? There has x and there's also a y. And that doesn't really help me solve what they are unless I get rid of one of the variable, which is what I'm doing here. If I can write y using x, then essentially I'm omitting one variable. So then what's left is we're going to plug this function y equals to 50 subtract half of x into the utility function. So we're going to say plug it into the utility function of x and y, which essentially is just a product of x times y. So then our life could really become easier and easier from there, right? So what I mean by that is, let's take a look at this utility function. It's x and y. Yes, but we're going to plug y equals to 50 minus half of x into this formula. So what that means is this becomes x times parenthesis 50 subtract half of x. So then we just gotta redistribute this x into every term of the parenthesis to expand the formula. So this becomes 50x subtract half x squared. Now, this is really just a quadratic formula. You can use whatever you want to solve it. You can use a calculator, you can use a formula, you can solve it whatever you want. So for me, I am going to set the derivative to 0, and then I'm going to solve for x by setting the derivative of u with respect to x equal to 0. So let's find u prime. So u prime here really becomes 50 because this x is just power of 1 that goes away. And then now I'm also have left with minus half, 2 comes up front, and this is x. And x really is to the power of 2 subtract 1, which equal to 1, which of course we don't have to write it. Now here, you might notice that this 2 and 2 cancels out. Lovely. Let's get rid of that. So I can erase this junk in front of it, and I'll write this x forward a little bit. So this is my u prime, and I'm going to set that to 0. So the idea there is because I want to know at what point does this utility function prime or derivative of the utility function no longer changes. So that is why I want to set derivative to 0, right? 0 means doesn't change. So set that to 0, which of course it's very easy math here. You can solve for x equals to 50. So there you go. Now that I solve for x, then I know the relationship between x and y, right? So I can also solve for y, which let's do that. So what's happening here is we can say y equals to 50 minus half of x, which in this case is 50, because we solve it here on the left-hand side. Then y becomes 50 subtract 25. So in the end, y, which gives us final answer to be 25. So now that we know x, we also know y. We know the utility, and when the utility is specifically at a maximum level that subject to this constraint budget B. So what's the final answer here, which is the final utility is equal to x times y, which of course is 50 times 25, and that gives you the final answer, 1250. So there we go. That's how we would have solved it conventionally, right? We're trying to use really simple algebra, high school algebra, to solve for the maximum utility, which, as you can see, it's pretty straightforward. You just gotta rearrange the formula and plug it in. Now, I want to talk about how to solve this systemically using the Lagrange multiplier. Now, this is when things get very interesting, because I read a little bit about this theoretical explanation, and it turned out the method of Lagrange multiplier is a technique in mathematical optimization for finding the local maxima and minimum of a function that's subject to certain constraints. So let's write down that statement. So that's what the method is supposed to do. Now let's talk about what it actually does, right? So it's working with tangent vectors. That's essentially what it does. It's working with a set of tangent vectors. So recall that earlier we have the utility function. So we have utility function, which is this letter u, that is a function of x and y. And then we also have budget, which is this letter b, that is also a function of x and y, where x and y are two of the variables. In the above example, we can think of it as two products. So now we can essentially abstract this by saying that you have utility function is just a function, and then budget is also another function, such that if the optimal point exists, then at that optimal point, the change of the first function with respect to certain parameters should be the same with the change of the second function with respect to the same sets of parameters. So essentially what I mean by that is this. Let's use a closed form mathematically to write this out rigorously. So there's this Greek letter called nabla, right? Let's write that down. It looks just like that. It's kind of like an upside down triangle. And what that means, this nabla symbol means that if you apply this symbol in front of a function, essentially what you're doing is you're looking at the changes of this function with respect to its parameters. So if I write nabla of u, what really is going on here is the change of function u, which is with respect to x and y, and this really gives you a set of partial derivatives. So what that means is partial u over partial x, partial u over partial y. So that's essentially what this nabla symbol is doing when you apply that in front of the function. So to give you guys a concrete example, if there's some sort of hyperbolic plane in a three-dimensional space that somehow look like this, and then let's assume that this is in some sort of three-dimensional space, then what this nabla u is really trying to say is the tangent of that plane at a certain dot. Let's pick a dot, right? Let's say you pick some sort of dot there. That's the point of interest. Then what you're really trying to do is you're trying to draw a hyperplane, which I'm going to try my best to draw it. It looks like that. And then let's give a shaded area to notice that this plane is tangent to the three-dimensional curve. So that's kind of the idea. It's a loose drawing. Essentially, what I'm trying to convey the message is that this plane at that spot is tangent to the three-dimensional hyperbolic structure. Now let's get back to our methodology. Let's see what this thing is doing. So once we understand this mathematical notation, nabla, then let's write out the Lagrange multiplier. So the Lagrange multiplier, obviously there's some sort of multiplier, right? Is expressed using the following closed form. Nabla of the utility function, let's say with respect to x and y, is equal to lambda times nabla of the budget function. Let's say it's with respect to also x and y. Now, this is a general form. So if you have a high dimensional function and you have x, y, z, or whatever other variables that you're using, this equation will also hold. But for the sake of this example, we're just going to use u and b in terms of same dimension as the above example. So really what's happening here is to lay this equation out in its most simple form in plain English, what we're really trying to say is, let's look at the utility function. At what point is the change of the utility function, right? That's what nabla is doing, right? Gradient means the change of the function with respect to x and y is somehow the same or equal to the change of this budget function at the same dot, x and y. So in other words, on the left-hand side, what we're really talking about here is the change of utility. And on the right-hand side, we're talking about the change of budget. Whatever magical dot, right, whatever magical pairs of x and y at x, y, let's call it star, right? At x star, y star, same on the left, same on the right. This has to be equal. So we're really setting this to be equal. And if you are able to set them to equal and also be able to find an optimal pair of x star, y star, then boom, you have your answer. And that's really how the story goes. And this works for all forms of formulas, not just U, not just B, any two formulas. But I'll have to read a little bit into that. I think there's some sort of premise that at least you need to be able to take the derivative of these two formulas. And I think there might be some other premise about the continuity. And then last but not least, let's not forget this multiplier, right? The method is named by this thing, so obviously we need to talk about it. So this multiplier also needs to subject to certain change. So also looking at the change of this multiplier. So with that being said, let's plug in the equation to this methodology, and then let's see what we're working with. So recall the utility function u, which is a function of x and y, is defined as a product of x and y, so x times y. And also recall our constraint function b of x and y, and this is equal to x plus 2y. We also set b to be 100, and these are all given as premises in the problem statement. Hence, we know and we done above that b can also be rewritten as x plus 2y equal to 100. And that is our constraint. So here, let's write that out. This first equation, that's our target function for optimization. And then this last equation here is the constraint. So those are the two functions that we need to plug into the Lagrange multiplier. So recall what we have above, right? The method says that nabla of utility function should be equal to lambda times nabla of the budget constraint. Then essentially what we're saying is left-hand side equal to right-hand side, which you can move around. You can say 0 equal to nabla of u subtract lambda times nabla of b. And the second equation should be able to hold. And we're going to use that as a key to help us solve this problem using Lagrange multipliers. So what we're going to do is we're going to use this calligraphic L, which is a function of x, y, and lambda. And we're going to define that as the two functions subtract each other. We're going to define that as the function u subtract the function b. So the utility function subtract the constraint function. Let's plug in what we know, x, y, that's utility function minus lambda times the budget function, which is x plus 2y minus 100 here. So at the optimal spot, it means that the derivative of this calligraphic L, right, the derivative of this function with respect to x, y, and lambda no longer changes. So what that means is we need to set the partial over x of this calligraphic L equal to 0. And that's our first equation. Let's say bracket 1. And then we do the second partial y, calligraphic L equal to 0. That's your second equation. And third one, you probably guessed, that's the last unknown variable, which is lambda. We don't know what that is, right? We gotta solve it. That also equals to 0. And this is your third equation. So then guess what? Here we have 3 equation, 3 unknowns. So let's write that down. This is 3 equation, 3 unknowns. And we can solve this systemically. So let's give that a shot, shall we? First, let's work out the first equation. So that's number one. And then we say that take a derivative with respect to x. So this becomes y, subtract lambda. And then notice that this y goes away. This lambda x is left with lambda. The second term, third term here, they don't really matter because there's no x in there. So we can just omit that. Now this is set to 0. Now what's the second equation? Second equation is taking with respect to y. So first one, we're left with x, and that's because this is the y here, and x is a constant, so it's left with that. And you look at the second term, x goes away, 100 goes away. We're left with this term in the middle, which gives a constant of 2 lambda. So that is subtract 2 lambda, and that's set to 0. Third equation from here, notice that this is with respect to lambda. Now the first term has nothing to do with lambda, so let's get rid of that. That's gone. The second term is lambda times this thing in the parentheses. So that's essentially what's left after you take a derivative with respect to lambda. So let's write that down. Here we have x plus 2y, subtract 100 is set to 0. So there you go. Notice that from here, the first two equations both have lambda inside, right? So why don't we figure out a way to get rid of the lambda? So think about it. This is 2 lambda, and then on top, there's just 1 lambda. If we multiply this by 2, then these two things can be canceled out if I just take the difference of the first two equations. So let's try that, right? We're going to multiply the first equation by 2, so that becomes 2y minus 2 lambda equal to 0. Now, this 2 lambda is exactly the same as this 2 lambda here in the second equation. So what we're going to do is we're going to take this pink equation, subtract this yellow equation, which is the second equation, to get rid of the 2 lambda. So what I'm having left over is 2y subtract x equal to 0. So this means that we have some sort of relationship between x and y. So 2y can be equivalent to x. And hence, that makes our life easier, right? Because look at the third equation. There's actually a 2y here. So if we know 2y is equal to x, why don't we plug that in? So we can kill off one more variable. So if you plug that in, x plus 2y, but 2y is x. So we can rewrite this as x plus x. And then let's not forget minus 100 equal to 0. And then you rearrange a little bit, it turns out that 2x is 100. And that means x is solved for 50. And then if x is 50, you can use the same strategy, plug x back into pretty much anything up here. I'm going to pick that one. Then you're able to solve for y equals to 25. And this should be giving you the exact same answer, right? The final utility is x times y. So that is essentially 1250 because it's 50 times 25. So there you go. By using two different methods, we arrived at the same answer. And even though in terms of this example, the second method seems like it took a little bit detour, but it's really making our life easier when these two equations take on more than two variables, because then we can solve systemically using matrix algebra. And there you go. I hope you like this video. Lagrange multiplier is a great method in the field of mathematical optimization. And I can 100% guarantee you guys, if you are interested in finance, specifically mathematical finance, in the future, if you're interested in portfolio theory, this method is going to come up again. So thank you for watching, and I'll see you guys in the next video.